So our topic today is about the solid solution and crystalline imperfections. Okay, metal and also ceramics. Okay, so there are many imperfections like uh, what is it? Interstitial substitution. Okay, even in catalyst also there is an imperfection. Okay. This is occur when sometimes we do the mixings between two metals. Okay, how can we know that uh, what is it? Uh, the metals can stabilize 100%. So there's a we have to follow the Hume-Rothery's rule. Okay, that's one we will discuss later lah. Um, Okay, so for this topics, we will discuss about the type of the solid solutions. Okay, because importance for the solid solutions, this chapter is going to be related with the chapter 8 for the solutions of the mixings of between two metals. Okay, only for today we will discuss about the type of the imperfections. Okay, or defects what is a 0D defects, okay, 1D defects, 2D defect, as well as 3D defects. Okay, 3D defect is something like we can see from our bare eyes. Okay, but for 1D or 0D is we cannot see actually. Okay. Defect in the crystalline solids like a point defect, line defect, or dislocation. Okay. So point defect, if you look at here that point defect is a 0D lah. Okay, something that we cannot see due to the like substitution or substitution or interstitial defects. Okay, line defects, dislocations. Okay, line defect is a 1D, 1D. Later we will discuss. Okay, so I hope that you can define what is the solid solutions. How can we calculate whether your between two solid or two metal, how many percentage that you can solubilize, or in term of the mixing, like, is it favorable or not? Is it 100% of the solubility like nickel in copper, or is it only 50% when you mix copper and zinc? How many percentage? Okay, we will define in for these solid solutions. Okay, we want to distinguish type of the solid solution. Okay. And we have to, I hope that later you can describe types of the crystal defects. Okay, and explain the influence of defects on the properties. Because when you mix things to uh, uh, two metals, okay, they will increase the properties of the materials, okay, or something like increase the mechanical properties, or the what is it, electrical properties, something like that. Okay. Okay. Uh, Actually, is in engineering. Okay, most of the engineering metals are we combine with other metals, ornamentals, because we want to improve their properties, right? Like electricals, uh, mechanicals. What else? Is it become more strong? Okay. Uh, like stainless steel, right? It's actually is that one is the mixing of more than two metals, right? Okay, we call it alloy. Okay, so we can increase the strength, higher corrosion resistance. Okay, uh, alloy, a mixture of two or more metals. This one, right? Two or more metals. Okay, all metals and non-metals. Okay, so even kalau the price is, of course, is higher for the alloy compared with the normal steel. Okay, because due to the corrosion or rusting. Okay, for the normal steel compared to the alloy. Okay, even if you want to, what is it, uh, we do for make a gate or grill, right? Okay, for your house. Okay, the price is really different. Okay, so it's no rusting for the alloy of stainless steel. Okay, so if you look at here, this is the example of the simple mixture of two alloy. okay, to metals, okay, like cartridge brass, this one, and binary alloy of 78% of copper and 30% of zinc. Actually, the percentage of uh, the solubility of copper in zinc is not really 100%, but it still can can achieve or optimum at higher temperature lah. By increasing the temperature, you can mix the percentage of solubility of copper in zinc can be increased by the temperature. Okay, okay. This one we will calculate how is it favorable or not. Okay, when we mix copper and zinc or other metals. Okay, say in Cornell is for the measure the temperature. Usually we call it thermocouple. Okay, this one I use also for my experiment to measure the temperature inside the reactor. Okay, there's a K type, S type, depending on the sensibility. Okay, so different type of the inconels is going to be different cost. Complex nickel based super alloy of 10 elements. This one. So especially when we mix two or more metals or non-metals, we want to increase the strength or increase the properties especially, but the problem is the defects. Okay, something like when you mix, maybe some atom is replaced by the parent atom will be replaced by the solid atoms. Okay, so we will define what is the solid and also host metal or host atom. Okay, so this one is the solid solutions. Okay, the dimensions. Okay, the simplest atoms, the simplest type of the alloy that contain two or more elements dispersed in the single phase structure. Okay, so if you look at here that generally the parents host. Okay, the host is like this one, right? This one is, I think the host is generally is zinc. Okay, and later we will see. I think it's copper. Okay, we add with the zinc. So for examples, solvent atoms, we call it also host or parent. So it's much greater. The number is much more, the atoms. Okay, and the red one is the atoms that we add to the solvent atoms. And this one we call it as solid atoms. Okay, so you have to remember. Also, this one is replace the vacant in parent atoms. Okay. And there are two types of metallic solutions. Okay, so if you look at here, that metal substitution and interstitial. Okay, substitution, the atoms, the solid atom will replace or displace the host of the atom. Okay, solid atom displacing atom of the host or solvent. If you look at here, this is the chromium, right? It's replaced the iron space. Okay, for the iron space, right? So it's replaced. That's why we call it substitute. Okay, substitute. Just replace. So iron is a host, and solid atom is a is it as a parent. Actually, the diameter is for the chromium is much larger than iron. Interstitial. This is just what is it? Uh, they locate space between the parent atoms or host atoms. Okay, solid atoms is located between atom of the host, meaning that there's a vacant here. If you still remember when we calculate atomic packing factor, right? Okay, there's a vacant space there. Okay, there's a vacant space like this one. Okay, there's a atomic packing factor, right? So for BCC, how many percentage? I think it's around 50%, right? Or 40%. Okay, so there's a vacant there. So it's replace the vacant space of between the parent atoms. Okay, so this space. Okay, because due to this small diameter, okay, small diameter or small size of the solid atoms, that's why they can located between the space between host atoms. Okay, for example, this one iron as a host atoms and solid as um, a solid atom is like a carbon. Okay, this one carbon. Okay, actually the diameters we can know, right? Okay, from the data you can refer to the handbooks. Okay, okay. So similarly, this one more detail about the substitutional solid solutions. Okay, solid atoms substitute for the parent solvent atoms in the crystal lattice. Right. Look at here that there's a vacant because of no host atoms. Okay. Crystal structure of parents elements remains unchanged. Okay, similar. Okay, there's no moving on the structure. Okay, there's still the same. Okay, except for interstitial, there's some movement on the structure. Okay, lattice may get distorted by the presence of the cell atom, especially in the atomic diameter differ significantly. Okay, so generally, if you look at here, this is a solid atom. This is a solid atom. Okay, when uh, the solid atom substitute the host atoms, okay, so maybe some there's a vacant lah. Okay, I'm not sure. In terms of interstitial, there's gonna be some another vacant lah. Okay, solid percentage in solvent can vary from fraction of the percentage to 100. Oh, it's meaning that from 0 to 100. Okay, 0 to 100. Okay, so this one we can calculate by using home rotary rules. Okay, whether we can uh, mix or not. Okay, between two atoms. Okay, okay. So what is the home rotary rules? Okay, so if you look at, you have to remember. Okay, the conditions that um, whether your two metals can be solubilized 100 or not, or maybe or 50%. So you have to follow this rules lah. We call it home rotaries. Okay, you have to remember this one. Okay, first we have to know the diameter not differ by more than 50%. This is the first rule. Okay, and then second, if favorables, we can move to the next one. Crystal structure of both element must be the same. So meaning that crystal structure we have, what is it? We have a BCC, SC, FCC. Okay. If what is it? Elements, first element is BCC and second one is FCC. The percentage to solubilize solute and parent atoms is going to be reduced, not 100%. Okay, maybe around 50% or 40%. Okay. Similarly, also in terms of diameter, but diameter is more important lah, because whether it can substitute your parent atoms or not. Space for the parent atom lah. Okay. Okay. And then the third one is similar electronegativity. Okay, difference meaning that electronegativity is not really difference lah. Later we will calculate this one. Okay, the how to get the difference in electronegativity. Okay, the lower difference in electronegativity is much better. Okay, if 0 is much better lah. Okay, not higher. Okay, and then this one, both elements have same valence, meaning that you have 2 plus and 2 plus. Okay, valence atom 2 plus and 2 plus 2 2 1 1. Okay, if not the same, the solubility is going to be decrease. Okay, this one is should be not in terms of electronegativity lah. Okay, not so really difference. Okay, sorry, not meaning that similar electronegativity lah. Okay, so this is the example. If you look at here, see the atomic radius is below than 50% for copper and zinc, right? Electronegativity difference is 0.1. Okay, how about copper and zinc? For what is the periodic tables? Copper and zinc is 2 plus 2 plus. Okay, is it the same elements? Okay, so but I think this one they have why the percentage is lower. I think is due to the difference in uh, in the crystalline structure. Number 2 is not favorable. This one is not favorable, I think. Okay, why is the lower? For Cooper and Plumbum or lead, if you look at here, I think another one is maybe due to the difference in the electronegativity or the valence. Okay, so we have to check from the periodic tables. Okay, because if you look at here, it's much lower than copper and zinc. Okay, this one is due to different, is only one. Okay, but this one we have to check. I'm not sure. Okay, I think it's a electronegativity is also is quite a difference. Okay, but still okay. I'm not sure in terms of diameter and also valence. Okay, and also crystalline structure. We have to check for the lead and also copper. Okay, but copper and nickels, if you look at it 100%, because the electronegativity difference is negative, and then it's below 50%. Okay, and if you look at here that even copper and nickels, I think have the same crystal structure. Later we will check. Okay, and same valence, of course. Nickel, copper have a same. Okay, to +2 lah. Okay, +2. Okay, same valence. That's why it's 100%. Okay. Okay, let's see the humidity for copper. Yeah, this one is for the copper nickels. Okay, so if you look at here, copper and nickels, how to calculate rule number 1, right? Diameter of atom must not differ, meaning that R solute, the diameter minus with the solvent divided by the R solvent times 100. So since the diameter is 0.125, 0.128 and divided by 0.128, so we can get negative 2.3. Okay, 50%. So then 15%, right? How about crystal structure? Both have FCC, right? Electronegative difference. This one you have to see from the periodic tables. So if you look at here, that 0.1, right? It's very favorable, very, very close. Okay, or almost 0. Right, copper and nickels. 1.9 and 1.80. So 0.1. Valence is the same, +2. So we can predict, okay, copper and nickel system very high solubility, 100%. Even if we confirm by using experimental, it's going to be highly solubility. Okay, this is in case of 100% solubility lah between copper and nickels. Okay, how about if you look at here that for the, oh yeah, this one is about copper and zinc, right? Below than 50%, 15%, right? Favorable, but FCC and HCP. Okay, so meaning that different in crystal structure, not favorable. Okay, in term of this one is favorable because it's electronegativity difference is not really high. Okay, not really difference. And this one +2. Only due to the only one is below than 50%, right? The solubility. But it can be achieved at higher temperature. Okay, maximum solubility. Okay, 38.3%. Meaning that if not high temperature, the solubility is also is much lower. Okay, so this is for the rule for the substitutional solid solution. Okay, you have to remember this Hume rotary rules. Okay, these 4 rules. Okay, kena ingat Okay. Okay, so let's see the interstitial solid solution. Okay, this one I already explained also. So solid or orange or impurity fit into space or holes between solvents. This one. Okay, solid atom are much smaller. If for examples like a HCONO. Okay, so if you want, this one is like an iron. Okay, iron. Oh, this one already. Okay, carbon or NO. This is much smaller. So interstitial solution, carbon in FCC gamma ion, okay, 0.075. While for the iron, this one is for carbon. See, this is the diameter, right? 0.075. That's why it can fit in the space between the iron atoms, right? Okay. So largest interstitial holes, meaning that they calculate this one, right? 0.053. Okay. So meaning that it can boleh fit lah sikit. Okay. A maximum of 2.08% of carbon can dissolve interstitially in gamma ion. It's not really high lah. Okay, but this one we call it as defect or imperfection. So from that one we can summarize that substitutionals and as well as interstitial solutions. Okay, foreign atom that replace host atom either in orderly or random arrangement. Okay, this one is for substitutional. For example, copper in nickels. Okay, this one is random. Order is nickel 3 and aluminum alloy. While for the interstitials goes into holes. See, this one holes. Random like silicon, carbon in ions. While this one is random. While order is a clays, ionic crystal, and also ceramics. Okay, you know the difference, right? Okay, if the solid atom their diameter is much smaller than the what is it the host atoms, okay, diameter of host atom, so it can be interstitial solid solution. Okay, so let's see we predict the example one. Okay, how to predict that this one. Okay, this is the element in copper. I think this is in copper. Using the data in the following tables, predict the relative degree of solute solubility of the following elements in aluminum, not in copper. Sorry, can we just change to the copper? Wait, why there's a copper zinc system? Copper, zinc, lead. Okay, it's okay. Can you predict based on the what is it? Based on the home unitary rules. Okay, can you predict, for example, if you this one is like aluminum, this one is for aluminum, copper. Number one, aluminum, mana? Aluminum, magnesium. This one is aluminum, zinc, aluminum, silicon. Can you predict? Okay, and then I think so you have to make a table like this. Rule number one, rule number two, and then paste in the Jamboard. I'll give you the link number. Can you do now? And then we can predict how much based on this one. Scale this one, very high 70 to 100%, high 30% to 70%, moderate 10% to 30%, 1% and very low is 1%. Can you predict? Okay, can you do? Take one paper. Can you predict? Calculate based on the this one, okay? Based on this one, similar, like this one. Is it favorable or not favorable? Just you guess or you just what is the expectation? What is the expected percentage? Okay, based on this following scale. If all follow the home rotary rules is if all is favorable, okay, you just make it state that maybe like for example like aluminium and copper, like aluminium and copper. Okay, rule number one, how many percentage? Rule number one is 2%. And then rule number two, rule number two is what? Rule number two, crystal structure, FCC, FCC. Okay, maybe. I don't know. This one, I have no answer. This one is aluminium. I have answer for the copper only. Okay, this one in the copper. And then three, four. Number four is electronegativity, maybe negative zero, En equal to zero. And then number four is plus two or plus n plus one or plus two lah. Plus two. So this one at the end, you can write here. This is very high, very high, very high. Right. Write the answer. It's just predict. Want to predict. Okay. Can you do? I give you the Jamboard ni. Jamboard. I give you about 10 minutes. The same Jamboard again. Please do first before I give you the link. Okay. Go to page 12. Go to page 12. This one I give the link. Okay, please do. Based on the home rotary rules. Just follow this rule. Okay. How can we get this electronegativity difference? We can get from here. This one, yeah. Yeah, this one. Different. I give you 10 minutes. I have no answer. Can you do? Aluminium copper R1 root 1 16 point. Anyone can add any row. Okay, thank you. How many? 4, 2, 2, 4, 2, 4, 5. 5. Okay, there's a 5. A, B, C, D, E. Okay, thank you. R2. Okay. Then what is the result? Your skill. Okay, can add. All of you can do. Want to choose which one? You want to calculate R1, R2 or R3 or R4? Number 3 rows. What is the scale? Aluminum. Okay. So 16.2, this is more than 50%, should be below than 50%. Right. So this is out. Favorable, not favorable, not favorable, not favorable. Okay, not favorable. Okay, thank you. FCC, favorable. FCC. Aluminum and copper, okay. This is not favorable. Aluminum and mangan. Cubic, okay, it's cubic, not favorable. FCC, aluminum and magnesium. FCC and HCP, okay, not favorable. Okay. Then aluminum and zinc. SCP, HCP, not favorable. Right. Okay, if you look at the tables. Silicon, aluminum and silicon also not favorable because it's diamond and okay. Okay, what else? Electronegativity difference, 0.3, 0.5, 0.2. Okay, still okay lah, 0.3. One okay lah. Okay, this one a little bit higher lah. It's okay lah, 0.3. How about rule number 4? Rule number 4. Valence. Same valence. Valence, this one, aluminium and copper. Aluminium and copper, +3, +2, right? +2, this one. Aluminium, silicon, +3, +4. For me, this one, if aluminium and silicon is the very lowest one lah. Okay, this one, not favorable. Even is very high, right? Look at here. Okay, can you make the scale? This one is very high, right?
Doktor,
Hmm?
ALCU tu kan, saya dapat 11.72.
Yang mana ni?
ALCU punya R1,
R?
R1
R1, aluminium,
Cooper.
Ya betul betul betul. Okay, sorry. Tapi 0.1 bagi dengan ni tak? Dia punya aluminium. Berapa persen? 0.128 minus 0.143 divided by 0.143. Okay, 11% right? This one. Betul? 10.5 lah. 0.5. Okay, sorry. So we have to delete lah. Betulkan. It's okay. Thank you. Okay. 10.5 lah. 10.5. So it's favorable lah. Okay. Okay. This one also not good. Balance okay, betul eh? So for me, what do you think? What is the scale? Number one. This one is favorable. Favorable is okay, but only this one not favorable. So for me, this one is only low lah. Ada tak yang high? 7.5 or much lower. If based on the what is it? Rule number one, this is much better lah because of diameter, right? Meaning that what is it? The diameter is much lower. Is follow the rule number one. Is an important thing lah. So for me is this one we can say as a high to very high lah. Okay, or we call it as high lah. High lah ni. Okay, high lah. For me this one is high. Then this one 10%. This one is maybe low to very low lah. This one low, very low. This one still okay. Still okay. Maybe this one is a high to moderate lah. High or moderate. High to moderate lah. Okay, high to moderate. We just predict, right? Maybe this one is low or very low lah. Very low. And this one 27, right? This one also maybe low to very low. And number 1% is maybe this one is okay, but this one is quite high. For me, can be considered as a moderate and also low lah. Okay, we can choose lah. Okay, either one. Okay. So we can say it's moderate lah because especially rule number one, right? Rule number one and also rule number two is follow the home rotary rules. Okay. So we can say moderate lah. Okay. This one is already out. This one is out. Okay. So low to very low is more possibility. Possibility is there. This one is maybe is okay. This one high to moderate. Okay, 7.4. And this one or maybe high to moderate also. This one is exactly is a very low lah. Or low. Okay. So we just put it. Okay. Okay, but if there's a question like this one, you just choose only one lah. Okay, there's no correct like a correct answer because we predict. But just make it logically lah. Okay, just choose only one like this one. Maybe you can say because two already follow. We can say this one is already moderate. Okay, low also accepted. Okay. Any question? But to confirm this one, actually we have to do experimentally. Okay, experiment. Okay, so you understand, right? How to use this home rotary rules. Okay, so we move to the example 2. Okay, if you look at here that for the example 2, calculate the radius of the largest interstitial void space in the FCC gamma iron lattice. Okay. The atomic radius of the iron atom, okay, is 0.129 nanometer in the FCC lattice, and the largest interstitial voids at the half zero zero, zero half zero, zero zero half type position. Okay. So actually this is quite tricky. Okay. So look at here that the plane is this one. What? This is the plane. This is the plane. So the plane is 0, 1, 0. See, this is the plane, right? 0, 1, 0, 1, 0. This is the plane. Okay. So if you look at here that have interstitial here, right? Okay. Why is it plane? So radius is gonna be R lah here. This is R, this R, and this one is equal to R lah. Okay, to R. Okay, for because diameter for the solid. Okay. So let's we do the we this one. Okay, just remember this one. You follow this one. Okay, and also look at here. This is the what is it? Lattice constants. Okay, especially for this one. Okay, this triangle. You can see this triangle. Okay, let's we do. Okay, so from the equation, okay, 2R plus 2R equal to A lah. Right. This one. This one. Okay. And then from that one also, this is equation 1. Okay. 2R square. Okay, equal to half A lah. This one. This one. Okay. So power of 2 plus. So this one is equal to half itulah. Okay, this one is question. Okay. Okay. So just substitute because this one is become just substitute to R into this equation. Okay. So we can solve. Okay. So 2R equal to 2A. Okay. Or we can solve solve. Okay. A is equal to just rearrange 2R. Okay, this is equation 3. Okay. So just combining equation 1 and equation 3, equation 1 and equation 3. So you can solve plus R equal to okay. So just solve for R. So equal to 0.414 R. Okay, so equal to 0.414 times with 0.129 nanometer. So you can get 0.053 nanometer. This is the answer. Okay. So the largest interstitial voids you can calculate. Okay. So that is a 0.053. Okay. Later I give you the tutorial or I think you can understand. Okay. You can visit this Jamboard anytime. Okay, for the answer. Okay, let's we continue. Any questions about the especially this one, laboratory rules? This one also important how to. I think in the textbook also available this example. Okay, you can see. Okay, let's see the crystalline imperfections. Okay, crystalline imperfections. Any questions before we move to the crystalline imperfection? You know, right? Okay, let's see. Okay, for the crystalline imperfection, just let you know that crystal is not perfect. Okay, they contain the defects or what else again? Irregularities in the structure, right? Okay. Uh, Defect critically determine many of the electrical and mechanical properties. So actually, when we mix together, as I told you, we can increase the properties of the materials. Okay. So actually, it can be classified according to the geometry and also the shapes. Okay. So as I told you, in there are 4 type of the what is it? The we can classify into 4: 0D, 1D, 2D, and also 3D. That ones you have to, because of different in the what to say, the dimension range of the defects, the size. Okay, okay. So if you look at here that 1D is 0D is a point defect. This one. Okay, we call it a vacancy. Okay, and then 1D is more to like lattice dislocation. Okay, so this one uh, we call it as a line imperfection also, or line defects. Okay, and then 2D area or interstitial defects. Okay, so these ones, look at here, this is an image from the when we took how to say, I think it's from the, I don't know, maybe like a SEM or TEM FSM, like a camera. Okay, you can see this one. Okay, or area defects. That's why this one we call it one line is 1D, area 2D. Okay, because we can see in 2D image. Okay, and then the last one is a 3D volume defects. Okay, like a crack, pore, we can see with our eyes. Okay, you know, so even if like what is it, the floor, right? You can see this crack or pore. Okay. So how about the dimensions of this all these defects? Okay, or the size? We can compare for the point 0 D lah, point defects, line defect. We call it also this one as a planar defect or volume defect lah. Area defect is also planar, we call it. So if you look at here that the smallest one is the atomic, around -10, 10 -10. Okay, the scale in meter. If we measure in meter, okay. And then second one is dislocation. Okay, line defects. And then the larger, much larger is interfacial defects or planar defects. This is a grain. Okay, twin boundary is what participates, right? And the largest one is the pore crack and crack inclusion. This is a volume defect. Okay, so this is how we differentiate differentiate according to geometry, shape, and also the size. Okay. Okay. So for the what is it the metals, if you look at here, how can we locate that or how can we distinguish that defects? If you look at here, this one, if atom missing, it causes a distortion of the planes. This one is vacancy, right? The green color. Okay. And then self interstitials. Okay. So interstitial is 1D, right? Based on the size, interstitials, interfacial defect. So this is planar defects. Okay, planar defects. Okay, meaning that 2D lah, interstitial C, cause distortion also. Okay, if you refer to this one, interfacial defect. Okay, okay, and then substitutionals. Okay, interstitials. Okay, this one is also this one you already discussed for the substitutional and also interstitial properties. Okay, so we already discussed it. Okay. Okay. Actually, there's another defect also. We call it as based on the cation and ion vacancy. Okay. Later we will see this one. Okay. Due to the vacancy, we call it Frankel and the Schwarzschild defect. Okay. Because it's depending on the stoichiometry. We want to make it the charge is the same. Okay. We call it a Schwarzschild and Frankel defects. Okay, before that, I will explain about the point defects. Is this one? Actually, is due to the plastic deformations. Okay, rapid cooling, particle bombardment. This is the example of the vacancy. Okay, this one also can form during the crystallization. Okay, so you have to know vacancy is formed due to the missing an atom. That's why we call it a vacancy point defect. Okay. And interstitial C, this one is interstitial, right? So is a what is it? They fill the voids. Okay, so it does not occur naturally. Maybe induced by the irradiations. Okay, also cause the distortions. Okay, this is a two type of the point defect. Okay, so another point defects is as I told you, is ionic crystals, Frankel and Schottky. Okay, you have to know that one. Okay, what's the purpose of these ionic crystals or cations and vacancy? Okay, if you look at here, that another type of point defects. How are they different from those in metals, right? Okay, actually they want to maintain the neutrality. Okay, they want to make it like you have two plus two, right? So you need -1 and -1, so that is become a neutral. Okay, some another one is for example, like you do if you still remember from the what is it, the ionic bonding, right? Okay, we want uh, the atom is stable. Similarly, also for the defects, we want to maintain the neutrality. Okay, so for the Frankel defects, okay, defect is created when the cation move to the interstitial side. Okay, if you look at here, that this one, right? This is a Frankel. Okay, because the ion is here, right? It's moved to this side, right? Okay. If two oppositely charged ions are missing, a cation and ion vacancy is created. This is Schottky defect. This one is Schottky defect. And this one is Frankel. This is missing. Okay, this one is moved. Okay, so impurity ions are also considered as a point defect in ionic crystal. This is we call it also stoichiometry defects. Okay, what to maintain the stoichiometry. Okay, we want to maintain stoichiometry and also neutrality. Okay, so let's see the in details. For example, like iron, right? In ceramics, Frankel and Schottky defect maintain 1:1 cation and ion step ratio. So meaning that neutral. Non-stoichiometry cation and ion 1:1 occur when one ion exist in multiple valence, meaning that if you look at here, this one is O2 O minus, right? O2 minus. This one is F2 plus. Okay, this one is F3 plus. Okay, if we calculate, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So we need another vacuum to maintain the to balance the number of ions. That's why there is a vacancy here for the F2 plus. Okay, if you calculate with the vacancy, it's gonna be a balance lah. The stoichiometry, the number of ions. But in terms of stoichiometry is not the same stoichiometry. The ratio is not 1:1. Okay, because the main purpose is to maintain the neutrality, okay, or balance the number of ions. So if you calculate uh, with the with the ion 2 plus here, okay, ion 2 plus is going to be more. Okay, so the number of ion is not balanced, or there's a non-neutrality. So this is uh, not good for your for this metal solutions. Okay, the main purpose is we want to neutrality and also balance the number of ion. That is the important one. That's why there is a vacuum here. Okay, so that is important. The main thing is balance number of ion. Okay, another one is what is it? This one already explained. Charge balance electronegativity. Okay, empty ions are non-stoichiometric defect cause unbalanced number of ions. Okay, so impurity can be atoms and ion and also cations. Okay, and ion cations is a non-stoichiometry defects like this one, right? Substitutionals. Okay, number substitutional cations. This one also to maintain the neutrality. This is another one. Okay, so for examples, okay, for example, this one, right? For the ion calcium 2 plus and Na plus. Okay, so if you look at here, right, 1, 2, 3, 4. For calcium, we need 2 Na. 1, 2, 3, 10. Okay. So when if you look at here, that this is a Cl minus, and this one Na plus. Okay. So there's if we want to replace with the Ca2 plus, okay, so we have to remove 2 Na lah, because this is a 2 plus ion. This one is 1 plus. Okay, so meaning that we have to replace with 2 ion of Na in order to maintain the neutrality. That's why here there is a vacant. Okay, okay. So replacing Na plus by Ca2 plus ion introduce excess plus 1 charge. Okay, charge will be balanced if another plus 1 charge is eliminated. So if there is another, if we did not remove the another Na plus, so meaning that is a more. Okay, so is a the number of what is it? It's not balanced lah in term of the stoichiometry. Okay, so it's not favorable. Okay, if we remove this one, if we remove, so it's become favorable. So it's become neutral. Okay, charge can also be can be balanced if we add 1 Cl minus ion to the lattice. Okay, non-stoichiometry occurs unbalanced number of ions. Okay, but the main goal is neutrality. Okay, so when we remove when we want to add Ca2 plus, okay, we have to remove 2 Na plus. Similarly, also for the anion impurity, this one cation. Okay, in ions for O2 plus. Okay, if you want to add O2 plus to the Cl Na plus, so we have to remove 2 lah. Okay, this one and also this one. Okay, because we want to add O minus. Okay, so it's balance. Okay, but in terms of stoichiometry is not non-stoichiometry. Okay, not the same 1:1 ratio. Okay, but it's neutral. Okay. Okay. Okay, let's see this video. Copy this in. Wait, stop and sharing. Share. That's the video.
In this module, you will learn about the various types of point defects present in the crystal lattice of solids.
I hope that you can hear the
Crystalline solids have a
sound.
regular arrangement of the constituent particles. However, this regular arrangement is sometimes interrupted by certain defects in the crystal, such as point defects and line defects. A defect arising due to the irregularity in the arrangement of the constituent particles around the single lattice point is referred to as the point defect. On the other hand, a defect arising due to the irregularity in the arrangement of the constituent particles across a row of lattice points is referred to as the line defect. In this module, we are going to explore the point defects, which are of three types: the stoichiometric, non-stoichiometric, and impurity defects. The stoichiometric defects are so called because they do not bring any change to the stoichiometry of the solid. These defects exist in the crystals of non-ionic as well as ionic solids. In the case of non-ionic solids, the stoichiometric defects exist in two different forms: vacancy defects and interstitial defects. A vacancy defect arises when a constituent particle leaves its lattice site, creating a vacant site in the crystal lattice. Alternatively, an interstitial defect arises when a constituent particle occupies an interstitial site in the lattice. On the other hand, in case of ionic solids, the stoichiometric defects exist as Frankel defects and Schottky defects. In both the Frankel and Schottky defects, the electrical neutrality of the substance remains maintained. Frankel defects arise in the ionic crystals having large difference in the size of the constituent ions. In such defects, the smaller ion dislocates from its lattice site to an interstitial site. Schottky defect, on the other hand, arises in ionic crystals having constituent ions of similar size. In such defects, equal number of cations and anions leave their lattice sites and create vacancies in the crystal. So far you have learnt about the defects that maintain the stoichiometry of a crystalline substance. However, there are certain defects that change the stoichiometry of a crystal. These defects are called non-stoichiometric defects. Non-stoichiometric defects are of two types: metal excess and metal deficiency defects. The metal excess defects arise due to two reasons: the presence of anionic vacancies in the crystal or the presence of extra metal ions. Let's first understand the metal excess defects that arise due to anionic vacancies in the crystal. When sodium chloride is heated in the atmosphere of sodium vapors, then some sodium atoms get deposited over the surface of the crystal. Some of the chloride ions diffuse from the lattice sites to the surface and combine with the sodium atoms to form sodium chloride. The electrons lost by the sodium atoms diffuse inside the crystal and occupy the sites vacated by the chloride ions. These sites are called the S centers. Such a crystal of sodium chloride, therefore, has an excess of sodium metal and thereby develop the metal excess defect. Let's now consider an example to explore the metal excess defects that arise due to the presence of extra metal ions. When zinc oxide is heated, some oxygen gas is released from it. The remaining extra metal ions and free electrons produced during the reaction occupy the interstitial sites, thereby developing the metal excess defect in the crystal. Now that you have learnt about the non-stoichiometric metal excess defects, let's learn about the second type of non-stoichiometric defects, the metal deficiency defects. The metal deficiency defects arise when a crystal becomes deficient of the metal on losing some metal ions from their sides. In such a case, to maintain the electrical neutrality, some of the remaining cations acquire extra positive charge by moving into the higher oxidation state. For example, in the crystal of ferrous oxide, a few ferrous ions move out from the site, resulting into a non-stoichiometric defect. Some of the remaining ferrous ions acquire higher oxidation state and become ferric ions. Let us now learn about the last type of point defects found in crystal lattices of solids, the impurity defects. An impurity defect arises when a cation leaves its site and some foreign cation occupies the vacated site. Such defects are found to occur in crystal lattice of sodium chloride when some lattice sites vacated by sodium ions are occupied by the strontium ions. To maintain the electrical neutrality of the crystal, one strontium ion replaces two sodium ions. So, half of the vacated sites are occupied by the strontium ions, while the other half remain vacant. Let's summarize what you have learned in this module. On the basis of their locations, the defects in the crystal lattices are divided into two types: point defects and line defects. Point defects are the irregularity in the arrangement of constituent particles located around one lattice point, while line defects are the irregularity in the arrangement of constituents in an entire row of lattice points. Point defects are of three types: stoichiometric, non-stoichiometric, impurity. In stoichiometric defects, no change occurs in the stoichiometry of the constituents. These defects are further divided into two types: vacancy and interstitial. Vacancy defects arise when a constituent particle leaves its lattice site, while interstitial defects arise when a constituent particle occupies some interstitial site. Non-stoichiometric defects lead to the change in the stoichiometry of the constituent particles. It is of two types: metal excess defects and metal deficiency defects. Metal excess defects arise either due to the anionic vacancy in the crystal or due to the presence of extra metal ions in the crystal. On the other hand, metal deficiency defect arises when a crystal becomes deficient of the metal. In impurity defect, cations in a crystal lattice leave their sites, and some foreign cations occupy the vacated site to maintain the electrical neutrality.
Okay, so that is about the defects. Okay, so let's we continue. I hope that you can have a clear view of picture about the defects, especially non-stoichiometry. Okay, what else? Interstitial substitutionals. Okay, and ion-cation impurities. That one also stoichiometry, but the main purpose is to maintain the neutrality of the electric charge. Okay. So we have almost 10 o'clock, so we just finished within 3 slides. Okay. So as I told you, the properties of materials, the important properties of the material is depending on the presence of defect or due to the presence of the defects. Okay. Actually, especially on the properties. Let me share.
Because it even works for people with low income. Of course, for high income earners,
Okay, so if you look at here, Many of the important properties of material are due to the presence of the defects. Okay, and then mechanical and electrical properties are sensitive to change in structure. For example, this one, the most sensitive is like electricals. Okay, yield strength fracture. Fracture is the mechanicals. Creep. Okay, semiconducting is the electricals. This one, density melting is almost or structure is almost insensitive. Sensitive. Not really sensitive. Okay, so let's see the significance of the point defect. If you look at here that in terms of the mechanical properties, okay, is increase the strength when we add zinc in the copper, right? This one 30%. If you look at here, the strength is become increased. Okay, so yeah, the purpose especially we want to increase the mechanical, especially the properties, mechanical and also electricals. Okay, and ductility also reduce. Okay, because we add zinc into the copper. Mainly also for the electrical properties. Okay, so when we add the impurities, if you look at here that the increase the electrical conductivity. Okay, so when we add nickel, this one. So when we increase, this is pure, right? And this one with the nickel, with the addition of the nickels. So the what is it? The electrical conductivity is increased. Okay. So similarly also for the germanium. This one is reduced. Sorry, germanium is increased. Resistivity is increased, right? So meaning that copper, when we add the nickels, so the resistance is increased. So meaning that reduce the electrical conductivity. But for the germaniums, okay, we add to the silicon is increase the electrical conductivity. Okay, so it's depending on which metal you want to add. Okay, whether you want to increase the mechanical properties or electrical properties. Okay, so this is the significant effect on the properties of the materials. Okay, any questions about this one? Actually, we finished for chapter 4. It's very short. Okay, and for the next class we will discuss on the, what is it, binary diagram, I think. Okay, phase diagram, phase eutectic and normal phase diagram. Okay, phase eutectic is for the metal. Okay, solid solubility. Any questions? Is it clear before we stop? QR code. Okay, QR code. QR code. Okay, if no questions, that's all for today. Okay, thank you very much.